Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to introduce the integrated rate laws. Let's get started. Instead of just slapping down what the integrated rate laws are, I want to show you where they come from. So let's take a generic reaction, A going to B, and let's first just write the rate law. So here is the rate law. Again, if we're monitoring the concentration of A versus time, again, we have a negative sign because that is a reactant. We write the rate law as so. This is what we generally call just our rate law, but actually this is the differential rate law. And it's important now to make that distinction because now we're going to talk about an integrated rate law. Okay, so we have this expression here. But what happens when delta gets very, very, very small? Well, when delta gets small, instead of writing delta, we're going to write D. So those of you who have taken calculus or are taking calculus will understand that once we move delta to D, it means that we can integrate. So let's rewrite our rate law like so. Now instead of deltas, we have D's, which means we can integrate this expression. Now before we integrate, we do need to define what the value for N is. So let's see what happens when we have a first order reaction. Of course, when we have a first order reaction, our N equals 1. So we'll plug in a 1 for this, integrate it, and let's see what we get. All right, so again, I just rewrote my rate law here again with my dA and my dt. So what I want to do first is I just want to do some rearranging. I'm going to need to move this dt over to the right-hand side, and I need to move my concentration of A over to the left-hand side, and I'm just going to go ahead and pop this negative over to the other side. So here's my first just rearrangement of everything. This puts my concentration of A with my dA and puts my dt to the other side. Okay, now this expression is ready to be integrated. Here is our integration. Again, we're starting from A naught to A, and we're going to go from T naught to T. Now, this expression here might not look so familiar on how to integrate, so let's make that a little simpler. Here we go, right here. So I've pulled out the 1 over A dA, so this might look just a little more familiar, a little more simple. And I also changed that T naught to 0 because our initial time is always going to be 0. So again, this is just a simplification here. Now, you may or may not remember, but when you're integrating 1 over x, this equals the natural log of x. That is, of course, the expression I have right here. So when I integrate this left-hand side, I am going to get the natural log of A minus the natural log of A naught. Of course, the right-hand side is very easy. It just integrates to negative KT. So this is our integrated rate law for first order reactions. The advantage of the integrated rate law is it's going to relate rate to time. So now we can do things like predict what a concentration is at a certain amount of time, or predict how long it will take to get a specific concentration. This is why it's helpful to have both the differential and the integrated rate law. All right, but this one is just for first order reactions. What happens if we have, say, a second order reaction or a zero order reaction? This table is going to summarize integrated rate law for 3 reaction orders, and these are the most common. So you can see here in my leftmost column, I have my value of N. This is your order. So you have your first order, your second order, your 0th order. You can see that is specified here in the second column. I also went ahead and wrote out the differential rate law. Of course, in our first order, our value of N is 1, so our rate is just K to the A. For second, we're going to have a squared term. And of course, for our 0 order, remember, anything raised to the 0 is 1. So our rate is simply K for our 0 order. We have already derived our rate law here for our first order. Here is our rate law for our second order, and here is our integrated rate law for our 0 order. So once you know what order your reaction is, then you can use your integrated rate law, again, to figure out anything that is time dependent, like how long it's going to take the reaction to get from an initial concentration to a specified concentration. And those are your integrated rate laws in a nutshell. I hope you found this video helpful, and thanks so much for watching.